Introduction to Integral Calculus. You can look at integral calculus as a coin, and a coin has two sides. One side of it is about the antiderivative, integration as an antiderivative, and the other side of this coin is integration as area of a plane region. So in this lesson, I will talk about this. Integration being about getting the area of a plane region. So how do you obtain the area of a plane region? Well, the areas of polygons, general polygons or regular polygons, can be obtained by dividing the region into rectangles, triangles, trapezoids, and summing up all the areas. So let us begin with something whose area we can easily get. Okay, so let's say, for example, for a rectangle. So the area of a rectangle is given by length times width. When it is a triangle, the area of a triangle can be computed in the following way. It is equal to 1/2 times the base times the height. If it is a trapezoid, the area is equal to 1/2 times the sum of the two bases times height. So these are the familiar polygons that we often meet in basic math, and we know how to compute their area. But what about your polygon? What about if your polygon is something like this? It is a regular polygon, but it has 10 sides. Okay, if you don't know the formula to obtain the area of a regular polygon, what we can do is we can divide this into 10 triangles. Okay, look at this. Each triangle has an area, and we know how to compute for the area of a triangle. So this one is going to be the area of this small triangle is going to be 1/2 times the side, that's our base, times A. A is the height. In regular polygons, we call this the apothem. So you can imagine it to be the height of this small triangle. So how do you then obtain the area of the entire polygon? This polygon is a decagon, a regular polygon with 10 sides. Well, we get the area of these triangles, and there are 10 of them, and then we will get the sum. And if you were to do that, what you will obtain is something like this: 1/2 times n, the number of sides, times the length of the sides, times the apothem. N times s is the perimeter. Okay? The length of the side times how many sides will give you the perimeter of your polygon. If a polygon is not a regular polygon, what we can do to get the area is cut it into triangles, trapezoids, or rectangles. We will obtain the area of each smaller polygon, and then we will get the sum of all those areas. So suppose, for example, we have this pentagon, 1, 2, 3, 4, 5, but obviously it is not a regular pentagon. So how do you get the area of this? Well, what you can do is you can cut this into 3 triangles, okay? This one, and that one. We will get the area of each of them, and then we will get the sum. So the area of this pentagon is going to be a sub 1 plus a sub 2 plus a sub 3. How do you obtain the area of a region which is bounded by curves, or bounded by, let's say, for example, bounded by one curve? So pay attention to this curve. This is the curve of a parabola. Okay? So let's say we are interested to know the area of the region that is bounded above by this parabola. Okay? Bounded on the sides by this straight line. Okay, x is equal to 3. x is equal to 0, and bounded below by the horizontal axis. So what you have there is a region that seems like a triangle, but not exactly like a triangle, because this is a curve. This is not a straight line. So this is what we can do. We can inscribe vertical or horizontal strips of rectangles or trapezoids into this bounded region. We will get the area of each polygon and obtain the sums or the sum of those areas. So the sum is going to be an estimate of the true area. Let us show it. Let us use rectangles. Okay, so that is one rectangle. That is another one. That is another one. We get the area of those three rectangles. We get the sum. That is our estimate of the true area of the region. But obviously there is an error. Okay, so this space here between the rectangles and the curve will represent the error. And by the way, this is how you write the idea of getting the sum of rectangles. A is equal to the summation of A sub I from 1 to n. In this case, I from 1 to 3. Okay, A stands for the area. Now, we can do better, okay? We can do better than this by choosing a different polygon. Let's say, for example, a trapezoid, okay? One trapezoid, the second trapezoid, and the third trapezoid. Now, look at that. It is almost like an exact fit. We get the area of each of them. We get the sum. That is our estimate for the true area of this plane region. Now, we can improve our estimate. Okay, and that estimate will go in the direction of the true area if we shall inscribe many strips of rectangles. Okay, look at that. N approaches infinity. The number of rectangles is going to be many. So if we were to do that, this is what's going to happen. Okay, get the sum of the areas of these rectangles, and that is going to be an improvement, a big improvement in our estimate for your area, because look at that. Okay, the error, okay, that vacant space there which represent the error is now smaller compared when we only used 3 rectangles. And so this is how we can do it numerically, okay? The area of the region that is bounded by that curve, okay? The horizontal axis from 0 to 3 is equal to this. A is equal to or approximately equal to the summation of the area, okay? But if you want to really get the true area, this is what you do. Get the limit of the sum as n approaches infinity, as the number of vertical strips of rectangles approaches infinity. So that is basically the idea behind integration as the area of a plane region. Okay? So for example, we have this curve. We are interested to know what is the area of the plane region that is bounded above by this curve. On the sides by these vertical lines and bounded below by the horizontal axis. What we can do is we can inscribe vertical strips of rectangles. Each rectangle represents an area, okay? Each has an area, and you know how to compute for the area. X times y, length times width. Delta x here means the length of the base of your rectangle times delta y, which is the height of your rectangle. We get the sum. So this is how we write it in integral calculus. The area is equal to the limit of this summation of, look at that, look at this, f of psi sub I times delta x sub I. You can look at delta x sub I as the base, the length of the base of your rectangle times the height of your rectangle. What is the limit of that? What is the limit of that sum? That is the integral. Okay? So using the integral notation, this is how you write it. The integral of f of x dx from a to b. That is how you read it. You call a the lower limit and b the upper limit. Example 1.1. Okay, so this is a numerical approximation of an integral. Estimate the area of the plane region R bounded above by this parabola. Okay, this is a parabola. It is bounded below by the x-axis from the interval -1 to 2. Okay. Okay, so I hope that you can see in your mind the plane region we are working on. This is it. Okay. It's not a polygon. Okay, that is the plane region we are working on. The true value of that area using the techniques of integration is actually 9 square units. Let us say, for example, we don't know it's 9, and we don't know yet the techniques of integration. Let us get the area of this plane region using numerical approximation. We will cut it, okay, we will partition this into 3 subintervals. So this is 1 interval, the second interval, the third interval. So this produces 3 rectangles. So in effect, if we want to approximate the area of this region, we get the area of the 3 rectangles. Okay, now why did I produce that midpoint? That is the midpoint. I'm going to evaluate my function at the midpoints. Okay, so this is going to be f of -0.5. That will give me that. Okay, look at that. 3.75. And then I will get the product. Okay, this is 1. Okay, the length is 1 times 3.75. That is the area of 1 rectangle. Okay, so let us do it. Let us obtain a numerical approximation of this area. So this one, 1, this is the midpoint. This is f of -0.5. 1 times that, 3.75 is equal to 3.75. So the area of this, the approximate area of this rectangle is going to be 3.75. With the second rectangle, what we did here is, again, the length of the base is 1, the midpoint is 0.5, f of 0.5 is 3.75, the area of this rectangle is also 3.75, but the cumulative area is now 7.5. We do it for the last rectangle. We get the sum. This is the sum. The true area of this plane region, okay, bounded by your parabola, okay, from -1 to 2 is actually 9. But this one is close to 9, 8.74. Let us do better, okay? Let us do it in a better way. And we can do it by increasing the partition, okay? Let us not stick to 3. Let us make it 6. 6, 1, 2, 3, 4, 5, and 6. Let us get the areas of each of those rectangles. Let us get the cumulative area. Okay, so this is the cumulative area or the cumulative sum. And look at that. It is now 9.06. Okay, so earlier our margin of error was something like 0.25. Okay, the true value of the area is 9. This one is 8.74. Using 3 partitions, our margin of error is 0.25, but by increasing it to 6 partition, we get something like 9.06. The margin of error is now reduced significantly to 0.06. So that is basically one idea behind integral calculus, to obtain the area of a region that is bounded by curves.